So thank you so much for joining us today. And we're going to start with the talk of Valentijn Karemaker about mass formula for supersingular abelian varieties. Valentijn, are you ready to go?
Yep. Thanks a lot, Rachel, for the introduction. And thank you to the organizers for putting together such a wonderful event. I've really enjoyed all the talks so far, and I'm very honored to be allowed to speak here myself. Also, congratulations on the book, which of course I got my own copy of immediately. It's really nice. Yeah, I was asked to speak about mass formulae for supersingular abelian varieties, and the results that I'm going to tell you were obtained in joint work with Fortaro Yubuko and Chafu Yu. But before I get to those, I would like to talk a little bit about the connections between these results and existing theories about supersingular abelian varieties, in particular about the moduli spaces. So there will hopefully be some nice connections to the talk by Gerard van der Geer this morning as well. And finally, I'd like to say that don't be disappointed, there will be a curve over a finite field at some point in this talk. All right, so let's start generally and fix an algebraically closed field K of characteristic P. And then, like this morning, we let AG be the moduli space over K of principally polarized G-dimensional abelian varieties. And we know this is irreducible of dimension G plus 1 over 2. And we can put various stratifications on it. So here's one. Start with an element X in the moduli space. So often as a notational shorthand, I'll forget about the polarization, but it is there. So for such an X, we can consider its p-divisible group over here. And we can consider it up to isogeny. And isogeny is a surjective map with a finite kernel, so it's somehow not too far from being an isomorphism. Then the isogeny class of the p-divisible group uniquely determines what's called a Newton polygon. And this gives us a Newton stratification of the moduli space AG. So where one Newton stratum consists of all the abelian varieties with isogenous p-divisible groups. And then a slightly less fine stratification is this one, since the isogeny class of the p-divisible group also determines an invariant of X called the P rank. So here's the definition. The P rank F is this number here, such that the variety X has P to the F P torsion points over K. And so we know that this number lies somewhere between 0 and G. And you can read it off from this Newton polygon that I just mentioned as the number of zero slopes. And this gives us then a P rank stratification, where a stratum consists of all abelian varieties with the same P rank. So there are G plus 1 such strata. Okay, but we're not really interested in all abelian varieties. We care about the supersingular ones in this talk, at least. So let me define what those are. Say an abelian variety is supersingular if it is isogenous, so same notion as before, to a product e to the g of some supersingular elliptic curve. So that means that this elliptic curve here is no p torsion. And we let SG then denote the moduli space of such things. So of principally polarized G-dimensional supersingular abelian varieties. So some things we can say about that. Supersingular abelian varieties have a unique p-divisible group up to isogeny, so a unique Newton polygon. That means that SG here is really a Newton stratum of AG, like the one we defined before. And in particular, since this Newton polygon determines the P rank, all supersingular abelian varieties have the same P rank, namely 0. And the converse, that P rank 0 implies that you're supersingular, is true for small dimensions, so for dimension up to 3 and not beyond that. Okay. Then we know that every component of SG has dimension the integer part of G squared over 4. This is due to Lee and Hort. And they also gave the number of components in terms of class numbers. Right, so I'm going to now define another stratification on this, for which I need yet another invariant. So throwing a lot of theory at you here in the first minutes, but please bear with me. So this invariant is called the A number. And the A number of an abelian variety, any abelian variety, is the dimension of the Hom space of alpha p into X, where alpha p is a finite group scheme, the kernel of Frobenius on the additive group. So this A number then depends on not the isogeny class of the p divisible group, but on the isomorphism class of the p torsion. So a slightly different notion. We know a lot of things about this A number. So for instance, if you have an abelian variety with p rank f, then we know that its A number lies somewhere between 0 and g minus f. And so then if we have a supersingular variety in SG, then you can show that the A number is somewhere between 1 and g, because this number f here is 0. And now we can look at the A number stratification of SG, where each stratum, SGA, now consists of all supersingular abelian varieties with the same A number. So due to work of Harshita, we know what the dimension of each A number stratum is. And he also gave the number of components, again in terms of class numbers. And secondly, Ord proved that the maximal A number case is somewhere special. So if you have A number G, maximum that it can be, that is equivalent to saying that the variety is super special. And that means that it's not only isogenous, but actually isomorphic to a product of a supersingular elliptic curve. And so by the line just above, we know that the superspecial stratum, SGG, is 0 dimensional. So it's just a bunch of points. Okay, and so this, as I said, the A number stratification depends on the isomorphism class of XP, but we can exploit this a bit further and give one final other stratification that is called the Ekerdal-Oort stratification. So you can define this again for any X in AG. Look at its P torsion up to isomorphism. Then there are various ways in which to describe this isomorphism class. For instance, it's classified by an element of the Weil group, WG, of the symplectic group, sp2g, or equivalently, due to Oort, by what's called an elementary sequence. So this then gives an Ekerdal-Oort stratification, which is indexed by these elementary sequences. And a bit confusingly, each stratum is usually called S sub phi. And so a stratum now consists of all the abelian varieties with isomorphic p torsion. So let me say a few things about this. That it follows from the definition, first of all, that the Ekerdal-Oort stratification refines the p-rank stratification that I gave you before. But in general, it's still open which Newton strata intersect with which Ekerdal-Oort strata and how. Secondly, you can also consider an Ekerdal-Oort stratification of the supersingular varieties by simply just intersecting each Ekerdal-Oort stratum with SG. And there's a combinatorial criterion, not too difficult, which determines when such an Ekerdal-Oort stratum is fully contained in the supersingular moduli space. But again, generally, the intersections of Ekerdal-Oort strata with SG are unknown. So we don't really fully understand when this intersection is non-zero. We know, though, by work of various authors, that the strata that are contained in SG are reducible, and that the other strata are irreducible. One more point, that the A number is constant on Ekerdal-Oort strata. As I said, this is also a refinement. So then each A number stratum is really a disjoint union of restrictions of Ekerdal-Oort strata to this. And again, general intersections of A number strata and Ekerdal-Oort strata are not so well understood. All right, so now I've given you 4 different stratifications. There were 2 that depended on the isogeny class of the p divisible group. That was the Newton stratification and the p-rank stratification. and also two others that depend on the isomorphism class of the p torsion, the A number stratification and the Ecuador stratification. So what happens now if you look for the isomorphism class of the p divisible group? That is the next thing we're interested in. So this should be somehow even finer. And this gives what's called a foliation of SG. It's in the title. So here's what we define. It's called a central leaf. It's again due to Oort. And it is the following thing. So for each x, which denotes an element of SG, we let lambda x be the set of all other elements of SG with isomorphic p divisible group. Okay. You can define this also for varieties in AG, but we're interested in the SG case. And we know that, we know that every central leaf is closed in an open Newton polygon stratum, and we know that every central leaf is contained in exactly one Eckert-Oort stratum. Now, there are in general infinitely many different of these lambda x's, but if you're looking at SG, then you proved that each of these is finite. Nevertheless, computing the cardinality is very hard. This is something like finding the sizes of isogeny classes of abelian varieties, determining all the isomorphism classes in it. This is a class number problem that is very hard to solve in general, but we'll solve a related question. And before I get to that question, I wanted to make another remark, which is that we can interpret this lambda x also as a double coset. So here's how that works. We have the automorphism group scheme Gx for such a point x in the moduli space, such that over any commutative ring R, the points on it are the following sets. So there are all the automorphisms that satisfy this criterion here, which is really saying that it's stable under the Rosati involution. So that it respects the polarization, in other words. And now one can show that there's a bijection between the set lambda x and this following double coset, where these are the adelic points on Gx, and this here is an open compact subgroup of the latter. Maybe one interesting thing to say is that Oort also showed that on irreducible components of Newton polygon strata, there is an almost product structure, meaning that up to a finite morphism, such a component is isomorphic to a central leaf times an isogeny leaf. So on the central leaves, the p divisible groups stay the same, and in the isogeny one, you're allowed to move with p Hecke correspondences. But we won't be needing that in this talk. So what is then the question that we want to answer? We finally got to it. Here's a quick recap of the definition of lambda x. As I said, computing the cardinality is hard, but instead we'll aim to compute the mass of it. And so this is what that means. That for any x in SG, we'll aim to compute the mass of lambda x, which is the sum over its elements weighted by their automorphism groups. So this is very much like a stacky count, as Van der Geer mentioned this morning. And by the double coset story that I told you just now, we can also interpret this mass as a volume, namely of the following coset of groups. All right, and so then we can ask, is there maybe something like a mass stratification of SG, which should mean that we identify regions on which the mass is constant. And we expect this to refine the A number and Eckert-Oort stratifications, because there you fix the p torsion up to isomorphism, and here we refine and fix the p divisible group up to isomorphism. So that is the ultimate goal. Now, from now on, I'm going to specialize to the case where g equals 3 and tell you what we've been able to do with that. We're currently working on g equals 4, but I will not touch upon that in this talk. And oh, I see a question in the chat about the third expression. Yes, so that is a notation that's sometimes used for an arithmetic mass of a group with respect to a certain open compact subgroup. So this is the open compact subgroup with respect to which you compute this mass. It's just in case you are familiar more with this notation. Thanks for the question. Right, so we'll do G equals 3, but before I get to the actual expressions for the mass, I'm going to tell you a bit more about the geometry of the moduli space S3, because we'll be using that in our computations. So that is the second part. If there are any more questions, please feel free to ask. Okay. So right, how do we describe the geometry of S3? That's what we start doing here. And so we fix for ourselves a supersingular elliptic curve whose Frobenius endomorphism is minus p. It's defined over fp squared. It is known that such an elliptic curve always exists. And we choose mu to be any principal polarization of E cubed. Okay. Then the following definition, which is again due to Lee and Oort, is of a polarized flag type quotient, or PFTQ for short, with respect to the mu that we fixed. And it is a chain of isogenes. So we have an isogeny here and another isogeny here, where we start with y2 lambda 2, which is a super special variety, this E cubed with this polarization P mu. And such that the isogenies rho 1, rho 2 and rho 1 satisfy these criteria here, and such that the polarizations satisfy the criteria here. I won't go much into that. The important thing for now to note is really that we start with something super special. And these PFTQs exist in any dimension, but like I said, I'm going to give the details for the G equals 3 story. So let's then P mu be the moduli space of these PFTQs. And then Lee and Oort show that this is a two-dimensional geometrically irreducible scheme over fp squared. And what is the precise relation between P mu and the S3? Well, here's a quick recap of the definition. It follows from the construction of a PFTQ that the last entry, so this y0 lambda 0, is principally polarized. So it's an element of S3. And so there exists a projection map from P mu to S3, where we just map the chain of isogenies to the last member. And here I've suppressed, on the left-hand side, I've suppressed the polarizations. And then we know that if you range over the various mu's that you have, so the polarizations of E cubed, then this map is surjective and generically finite. So the thing to remember then is that each P mu is as if it is a geometrically irreducible component of S3. So if we want to study all of S3, it's enough to look at the various P mu's. I should also remark that P mu is in a sense independent of the mu that we choose, because there's only one isomorphism class of P divisible groups for E cubed. Right, but now we've translated our problem of understanding the geometry of S3 to understanding that of P mu. So what can we say about this P mu? And here we finally have a curve of a finite field. So let's see the Fermat curve over P given by this equation over here. So it's a Fermat curve in P2. And we know a lot about this curve. We know its zeta function, so we know the number of points that it has over Fp and over all the extensions. We also know its genus, P minus 1 over 2. And we know that the points admit a left action by this unitary group, U3 over Fp squared. And the reason this now comes into the story is that Lee and Oort show that we can see this P mu as a P1 bundle over the curve C. So it's a vector bundle of rank 2. And it admits a section. So there's also a map going the other way from C back to P mu, and we call the image of that section T. And now, what do we have? Well, first of all, for each x lambda in S3, there exists a polarization, mu, and a PFTQ, y, so a chain of isogenies corresponding to this mu, such that the projection map sends this y to the class of x that we started with. So we can always find, for every variety, we can find such a flag type quotient. And this flag type quotient in turn is uniquely characterized by a pair of two parameters, t and u, that come exactly from this structure of a P1 bundle. So t is a point on the Fermat curve. So it's a projective point with three coordinates, t1, t2, t3. And then the point u is a projective point, the projective line that is the fiber over this point under pi. And this will be very important because our mass formulae and hence the mass stratification that we'll find will depend heavily on this pair t and u, or in particular on the field of definition of t and u. So with this in hand, we can also put some sort of a number stratification on p mu that will make our analysis a bit more tractable. So recall that I said the a number of a variety is the dimension of this Hom space of alpha p into x. And now if we look at a chain of isogenies, so at a PFTQ, then we say that its a number is the a number of the last member. So the a number of y0. Okay. Then also recall that for a threefold, we knew that the a number is between 1 and 3, so it's either 1, 2, or 3, and that this highest a number, 3, was exactly equivalent to being super special. Okay, so what about the flag type quotients? Then here there's a bunch of facts. I should say these facts are also all due to Lee and Oort. And the first one is that if your flag type quotient is in the image of the section, so this image over here, then the a number is 3. So that is a very special case. Now it's going to disappear, but the next fact is also due to Lee and Oort. So if the point t on the Fermat curve, that is your parameter for the flag type quotient, if that is defined over fp squared, that is exactly equivalent to the a number being at least 2, so either 2 or 3. For any point in the fiber over this t. And so then a number 1 happens when these two things don't happen. So for a PFTQY, we know that it has a number 1 if and only if y is not in the section, image of the section, and it does not project down to a point on the Fermat curve over fp squared. Okay. So to illustrate this a bit, I've drawn this very nice high-tech picture for you. So here we have p of mu. That's this the square over here, and it maps down to c with the map pi. So this is our Fermat curve, and the section here is t. So we know that everything on this red line here will have a number 3. Now, if we draw the fp squared points on c over here, so just the points, then the fibers over those are the blue lines. And we saw that the a number on the blue lines is at least 2, so 2 or 3. And then everywhere else, so in all the white regions, we have a number 1. So you can see very clearly from this picture that a number 1 is really the generic case. This is what's happening most of the time. And so the previous slide and this picture show us that the a number really tells us where we are in the p mu. So in particular, it will give us restrictions on where t and u live. Right? So how are we going to use this? And now we can use the flag type quotients to construct what are called minimal isogenies. So we know that any supersingular abelian variety X admits a minimal isogeny of this form. And so it's a map 2X from a super special abelian variety Y. So minimal here means that any other isogeny coming from something super special has to factor through this phi. And dually, there's also the notion of minimal isogenies to a super special abelian variety, but we won't need that in this talk. And so the idea is to construct minimal isogenies for the X that we're interested in from a PFTQ that lies over it. So we saw that we can always find such a thing, and we can construct the minimal isogeny from it. again, using this crucial observation that Y2 is super special. So again, I'm going to separate a few cases based on the A number. So if the A number is 3, then we know of X, then we know X is already super special. And so, of course, the minimal isogeny would just be the identity, because that's the minimal map. If the A number is 2, then you can show that the A number of Y1, the one in the middle, is 3. So this one is already super special. And so this first part of the flag type quotient is then the minimal isogeny. Whereas if the A number is 1, which was the generic case, then we need the full flag type quotient for our minimal isogeny. So those are all the results that we'll need. But now let's finally get back to our goal of computing these masses. In particular, computing mass formulae. So our goal was to compute the masses of the sets, the central leaves lambda x for any x in S3. And we want mass formulae, which means basically just a nice expression for this mass. To make that a bit clearer, here's an example of a mass formula, a very famous one by Eichler and Turing, that says that if you look at elliptic curves, then you let your set S be a set of all supersingular elliptic curves over FP bar up to isomorphism, then the mass of this set with the weighted sum by the automorphisms is P minus 1 over 24. So a very neat expression. And since there is only one central leaf in this case, this gives us a mass stratification of the supersingular elliptic curve. So there is one mass strata. A mass formula for Abelian surfaces, so the two-dimensional case also exists. That is due to U and U and to Ibukuyama. And so the case of S3 was really the logical next step for us, where we can also use all of the theory that we've just seen. So here's how we're going to use the minimal isogenies that we just constructed. Start with any supersingular variety and let this phi be the minimal isogeny 2x. Then we can write x tilde as y with the pullback polarization. And we have this automorphism group scheme g of x for any point x. But now using the minimal isogeny, we can view both the g of x tilde of z hat and the g of x z hat as open compact subgroups of the same adelic group. And moreover, they differ only at P. So at all other primes, they are the same. And we really only care about what happens at P. And this is a very useful fact, because what we can then see is that the mass for lambda x, the x that we're interested in, is really the mass of the x tilde up to this comparison factor here, which consists of indices of these automorphism groups. And since, like we said, it only differs at P, the comparison factor is really just one index of the automorphisms of the P divisible group of X in that of Y. So in other words, we can compare any supersingular mass to a superspecial mass. And the reason that this is useful is that all of the superspecial masses are known. Otherwise, we would still not be anywhere closer to our goal, but they are, and they are known, in fact, in any dimension. So it's due to, this result is due to many people who have written their names. And I've summarized it in 2 points. So suppose that we have a superspecial abelian threefold, x tilde, then it is either principally polarized or not. And I said before that we're interested in S3, which is all the principally polarized varieties, but it turns out that we're going to need this second item later on. So if our superspecial threefold is principally polarized, then the mass of lambda x is the following expression. And here we should note that lambda x really is the set of all isomorphism classes of superspecial abelian varieties with the same kernel of polarization. So there's only one such lambda x for this particular principal polarization. And similarly, if the kernel of polarization is alpha p times alpha p, then there's again only one central leaf, and we know what its mass is. Right, so now that we know the superspecial masses, it remains to compute these comparison factors in all the cases we're interested in. And we're going to do it by a number, but because of this point over here, we don't need to do the a number 3 anymore, because that's already super special. So we're going to do a numbers 2 and 1 in that order. And I should say that in the paper, we use the language of Dieudonné modules instead of these cumbersome automorphisms of p-divisible groups. But I've left those out of the story today. It does make everything very nice and explicit. So we really write down bases for these modules and manipulate them explicitly. But I'll try to give you an idea of what happens in the next few slides. So let's start with the a number 2 case. Like I said, start with an x that has a number 2. Then let's consider a flag type quotient over it. Then this is characterized by a pair t comma u, like any flag type quotient. And the t lives over fp squared, because we said it's a number at least 2 when it lives over fp squared. And u is not defined over fp squared, because then we would actually have a number 3. So you can show this is the pair t comma u that we need right now. We also saw that the minimal isogeny was just this first part. And so the comparison factor that we need to compute is the automorphisms for x inside those of y1. Okay, the idea is then to reduce. And this reduction is really reduction modulo the skeleton of the Dieudonné module, but it comes down to reducing to fp squared. So we can reduce the endomorphisms to matrices over fp squared, and then the automorphisms over here map surjectively to SL2 over fp squared. And those for x, on the other hand, reduce to SL2 intersected with this end u cross. And end u is really just the image of the endomorphisms of x under reduction. But what it is explicitly is written over here. So the endomorphisms of u are all the 2 by 2 matrices over fp squared that send the vector u, remember that's u1 and u2, point on the p1, to a multiple of itself. And there are 2 possible things that could be depending on the field of definition of u. So if u lives over fp to the 4, then it's fp to the 4, and otherwise it's fp squared. And so then we can show that this intersection here is either fp for the norm 1 elements, so elements alpha, such that alpha times alpha to the p plus 1 equals 1. If u lives over fp to the 4, and plus minus 1 otherwise. Okay, so then we're almost there. Because by surjectivity of this reduction map, which is something that we had to prove, then computing the index of automorphisms that we're interested in, it's the same as computing the index on the reductions. So we just have to compute the index of this intersection in SL2 fp squared with the whole of SL2 fp squared. And again, there are 2 cases depending on the field of definition of u. And so then we're done. We can show that this y1 is not principally polarized, but it is super special. So we're going to need the second point of the super special mass that I showed you. So we have that super special mass. Here we have the comparison factor, and then we just put the things together. So that gives us the mass formula here. There are 2 mass strata on a number 2. I hope for me, it's falling off the page a little bit, but in any case, there's still the same case distinction that we had before over here. And the precise expressions are here, where I should add that E of P is not very complicated. It's either 0 or 1. It's 0 if P is 2, and 1 if P is greater than 2. Right, so that was the a number 2 case. what about the a number 1 case? So here we start over again. Now we have a point in S3 with a number 1. Then again, its flag type quotient, a flag type quotient over it, is characterized by t and u, where now t does not live over p squared. So it lives on C0, which is the curve minus the fp squared point. And u can a priori be anything, so it lives anywhere over k. We also saw that in this case, the minimal isogeny is given by the full flag type quotient. And so the comparison factor that we need now is that of x, automorphisms of x, inside those of y2, so all the way to the top. We're going to need a little bit more notation in this case, but I've tried to keep it light. So let dp be the division quaternion algebra over qp. So here, this qp squared, with that I mean the fraction field of the width vectors over fp squared. With this element pi, satisfying pi squared equals minus p. And let O of dp be the maximal order in it. Then we prove the following things. So the group G2, which is my shorthand notation for the automorphisms of the p-divisible group of Y2, that is like a unitary group. They're matrices, 3x3 matrices over ODP that satisfy this unitary condition, where the star is the canonical involution on the quaternion algebra. And inside that, we have G for the automorphisms of X, and those are all the elements of G2 that send X to itself, basically, send the p-divisible group to itself. And note that here we do not have to specifically say what happens to the polarization, because you can show that's automatically taken care of. Right, then again, the idea is to reduce. And now we reduce modulo P, which really means reducing modulo P times the Giordani module of Y2. And you need to show that this is something that you can do and that it's well defined. But it is, and then we obtain the reductions of these two groups. And we also show what they are. So the G2 bar is the reduction of G2. Those are matrices of this form, so A plus B pi, where A satisfies a unitary condition and B satisfies a symmetric condition. So this is enough to then determine the cardinality of G2 bar as the product of the sizes of unitary matrices and symmetric matrices. So we know this really completely explicitly. And G bar a priori are the elements of G2 bar that send the reduction of X to itself. This is abusive notation, but I hope you understand what I mean. Right, and again, by surjectivity of the reduction map, I hope this doesn't fall off your screen, the comparison factor that we're interested in of these automorphism groups is the same as the index of G in G2, and that is also the same as the index of G bar in G2 bar. So to really work out what this is, we need to know more about G bar, because here I've only said the elements that send the reduction to itself, but what do they look like? And so that's what we did next. Here's a recap of what we're trying to do. So this factor that we need is really the index of G bar in G2 bar. And we showed the following thing, that the elements of G bar can be written in the following form. So here we have a matrix A, that is a unitary matrix. And down here we have the matrix A, where each of its entries is raised to the pth power. And here we have 0. And here we have SA, where S is again a symmetric matrix. And moreover, the matrix A has T, the point on the Fermat curve, as an eigenvector with some eigenvalue alpha that comes back here. So here we have a condition on S that we can see depends on T through this alpha, and it depends on U, the point U, which is coordinates U1 and U2 over here. So this psi T is a homomorphism that I can write out for you, but I will not in the interest of time. The most important thing is that you can see where T and U play a role in this description. Now we see that the images of these maps for varying t, they define a horizontal divisor in C0 times P1. So this is a trivialization of P mu. And if we let for any t dt be the dimension of the image of psi, and dt be the intersection of d with the fiber over t, then we can show when this thing here is in the image of psi t, namely u is exactly inside this dt by definition if u inverse is in the image. Okay, I know this is a bit technical to parse, but this allows us to compute the cardinality of G bar. Because what do we need to compute? We need to see how many of these unitary matrices there are, such that this thing is in the image, and we can count those, then we multiply by the size of the kernel. So we really study this term dt, that is actually a separate chapter in the paper, because it depends on the degree of t over fp squared. It's always something between 3 and 6, and we have a pretty good handle on when it's what. But the main thing then is that we see that there are 3 cases, and they depend on t and u in the following fairly explicit way. So here again, E of p is either 0 or 1. It's greater than 2. And we see the dt coming back here. So this term here is the dimension of the kernel, or the size of the kernel of psi t. And again, now we are done, because we know the super special mass that we start with. We want to compute the comparison factor, but we know the cardinality of G2 bar, and we know the cardinality of G bar. So again, we just put everything together and see what we get in the end. And the main thing to note is that there are 3 mass strata in the A number 1 stratum of this 3. And we really have a very concrete description of the mass. So now we're very happy. We've done what we wanted to do, find a mass stratification of S3. But maybe you wonder, now we've done all these computations, can we also use them for something else? And that is the last thing that I wanted to tell you today. Yes, we can use them to say something about Ort's conjecture. So what does Ort's conjecture say? It says that every generic G-dimensional principally polarized supersingular Abelian variety over K of characteristic P has automorphism group C2, so just plus minus 1. This is as small as it can be. And this is a logical thing to conjecture because the same is true for ordinary Abelian varieties. So if you replace supersingular with ordinary, then this is known to hold. However, we know that this conjecture does not hold in general. And there are counterexamples due to Ibukiyama and Ort himself. So they gave counterexamples in dimension 2 and 3, but note that the characteristic was P was 2 in both cases. And so this is what we then prove using our computations, is that when the dimension is 3, Ort's conjecture holds precisely when the prime is not equal to 2. So some notes about this. Generic, this word generic up here, in general means that the map from spec A to SG factors through a generic point. But for us, it means a few things. So the A number is 1. We saw that this is a generic case. And the factor quotient over it, T and U also have to be generic, which means that T does not live over FP squared. That also follows from the A number 1 thing. And U is not in this particular divisor DT, because that is a very non-generic case. So in that situation, our computations and a few more show exactly what the automorphism groups are. So if the prime is 2, if the characteristic is 2, then the automorphism group of such a thing is 3 copies of C2. And if it's not 2, then the automorphism group is C2. So I wanted to end with that, and thank you very much for listening.
Wonderful. Let's see, are there any questions? Valentine, do you want to also say, I mean, when G equals 2, this is resolved also, right?
Yes, that's true. Yes, but given that I was talking about the dimension 3 case, this is what we got. Yeah, that's true. Thank you. And yeah, we mentioned some of this in our joint paper, Rachel and I, what happens in general, like a heuristic.
Wonderful. Let's see, any other thoughts or questions?
Gustav?
Yeah, I raised my hand.
Oh, I'm sorry, I'm not good at seeing the hands. Okay.
Sorry.
Yeah, Christoph?
Yeah, just, I mean, to see in comparison with what Van der Heers said this morning, I mean, when the genius and the n was growing, then, I mean, things started not to be polynomial. I think from what you say and the type of computation you have, I mean, you will never encounter this problem. I mean, your mass formula are always going to be polynomials in P.
Yes, that's right. So yeah, we are actually looking at the maximal degree of these things, and or when the maximum of this polynomial is obtained, sort of in a more analytical way. But it's true, yes, we don't have this problem that we get these weird modular forms that are not rational in our expression. So I guess this shows that the moduli space of curves is more weird than the moduli space of Abelian varieties in a sense. Yes.
And I have also a second one. I mean, in the papers that Everett Howe mentioned yesterday with Henrik Knott about like isogeny classes in Genus 2, I mean, where the Jacobians are in Genus 2, we used one result about the mass formula for supersingular where you could like not only know that, I mean, you have like some supersingular Abelian varieties, but you had some supersingular Abelian variety with a precise automorphism group. And I was wondering if your formula for Genus 3 could say also, I mean, decompose according to the automorphism group.
It's a step towards it, but it's not good enough yet, I think, because when you know the mass, then you know there are a few, okay, once you know the mass of such a lambda x, then there is a finite number of possibilities for the cardinalities of the automorphism groups so that these things add up to the right mass. But in order to prove that really certain automorphism groups occur, you need to explicitly construct a variety with this automorphism group. This actually happened in our Genus 4 work so far, is that we knew what the mass was, and we had a suspicion that it's probably two varieties, one with this automorphism group, one with this other. But to show that was actually a whole lot of extra work. So in some cases, yes, the mass can directly tell you the existence of certain automorphism groups, and some you need to do more work to exhibit them.
Because somehow the denominators tell you something. I mean, you know that if you have a denominator, you should have like a group of order 5 or something like this, which appears somehow.
Very true, yes. So then, because of that, you know quite a few things about the various finitely many options that you have. And for instance, it's sometimes good enough to show that there must be more than one variety in your lambda x, or not, that it's really a central leaf with a unique point. But yes, again, in general, that's not always enough.
Thanks.
That's a good question. Thanks. Sumya has a question. I see a raised hand from Sumya.
Yeah, hi.
Hi.
Okay, so for the genus 4 case, do you have a nice description of the P mu, like analogous to the P1 bundle over the Fermat curve situation?
Yes, there exists a similar description is in the same book by Lee and Ort. But then here there are two equations. So I think they actually give equations for any dimension, or they show at least how you could find them analogously in any dimension. But yes, that is known. It's just more cumbersome to work with, and there will be more different cases to consider, different regions in the space. But you can do it very much in the same way.
Okay, awesome. Thank you.
Yeah. Happy to send you the precise reference afterwards. I have it somewhere over here on the.
Okay, thank you.
Oh, yes, I also had a question. You may have said this about the A number 2 calculations. Can you separate them into the 2 different ectal ort types for A number 2?
That is something we did not try to do. Probably we can, but it was somehow not necessary, because in the A number 2 case, really it's like you can more directly use the computations that were done for the surfaces. So we just used those directly, and that gave us our answer. But I guess if you wanted to refine it, we could. Yes, that is interesting. We should look into that. Right now for genus 4, that is definitely how we're proceeding, by fixing an ectal ort type first and looking at that stratum. So singling out one of those at the beginning instead of working with the whole A number stratum in one go. Thanks.
Wonderful. Okay, well, let's thank Valentijn again.
Thank you.
And we will start back on the hour in 9 minutes.